Alright, so in this video, we're going to be talking about the three equations that we can use to describe a plane. Alright, now for the equation of a line in three dimensions, okay, what we needed was a point on the line and the direction of the line. If we try that same logic with a plane, what ends up happening is, well, here, I'll show you, okay? If we just try to describe this with a point on the plane and the direction of the plane, okay, it could be this plane or anything else rotated kind of around that axis that we kind of just created, okay? It could be a point that's, going in and out of the board here, because that still has a point here and it can go in this direction, okay? So, that's kind of the idea here. We're not going to be able to just describe it with a point and a direction, okay? What we need to do is we can describe it with a point, but we need a normal vector, okay? So we describe a plane with a point and a normal vector. Now the point, okay, that point is going to be the vector r naught. That will be x naught, comma y naught, comma z naught, okay? That's just the same thing as when we did the line equations. Now, we're also going to have a normal vector, and if you're not familiar with that, I kind of forgot that not everybody's going to be familiar with that term. Okay, the normal vector is just going to point orthogonal, or you can say perpendicular, to the plane. Okay, so if the plane is this whiteboard, the normal vector will either point out of the board or directly into the board. Okay, so that's the normal vector. And also note here that the r vector, okay, that's going to be the same exact thing as it was with when we talked about our line equations, which is the vector x, y, z. Now let's move on and find the first equation that we can use to describe a plane, okay? So everything, these two black vectors and this one blue vector are all on this one plane right here, okay? You have this position vector r naught, okay, which is pointing to this point right here. It's this position vector right here that's pointing to the point x naught, y naught, z naught. And you have your vector r pointing to the point just any x, y, z, okay? And if you find the vector you're going to start from r naught and go to whatever that r is going to be, you end up with the vector r minus r naught, okay? And since this is all happening on one plane, the vector that is normal to it, okay, the vector that's normal to it is going to be perpendicular, right? Because that's what normal means, right? It's going to be perpendicular, all right, to that vector, r minus r naught. So if you take the dot product, you do n, the normal vector, dot the vector r minus r naught, you will get 0. And that right there, that is our first equation, okay? And that is called the vector equation of a plane. Okay, and how you remember that? Well, that's the only equation with vectors in it. Okay, that's how you can at least pair up the name with the equation. And that being said, this really isn't an equation that you need to memorize either, as long as you kind of understand this picture and you understand that the dot product of these two vectors is going to be 0, because that's literally your equation. Okay, you're saying that the dot product of these two things needs to be 0. Okay, because these two things are orthogonal, so their dot product must be 0. Now, let's just start writing things out here. We know our normal vector is a comma b comma c. We're going to dot that with our vector r, which is x, y, z. And we're going to subtract r naught, which is x naught, y naught, z naught. Okay? If we do that, we get the vector ABC. We're going to dot that with the vector, we have x minus x naught, comma y minus y naught, comma z minus z naught. Okay, just doing some vector subtraction there. We have to do x minus x naught, y minus y naught, and z minus z naught. Okay. Now, we try to find our dot product here. All we have to do is multiply the components now. We have a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And that, of course, is going to be equal to 0. Okay? that's still going to be equal to 0. This is our dot product of these two things, kind of just all drawn out. And, well, that's going to equal 0 still, because this n and the r minus r naught, they're orthogonal. Okay, these vectors are orthogonal. So the dot product is still equal to 0. And right here, what you get, this is called the scalar equation. This is called the scalar equation because, well, what do you get out of a dot product? You get a scalar, okay? You get a scalar answer. So you can kind of think of it, that's why this is called the scalar equation. All right? And if you know your vector equation, you don't need to memorize your scalar equation. You know, you can if you'd like to, but you just find the dot product, okay? You know what n is, you know what r is, you know what r naught is. You can write that as, you know, ABC, x, y, z, and x naught, y naught, z naught. And there you go. You compute your dot product, you get this. Next, we have one more equation left, and all we need to really do is distribute this a, b, and c. We get an ax minus ax naught plus by minus by naught plus cz minus cz naught, and that's going to equal 0. Now, one kind of thing to hit on here, okay? Here are things that are constants in this equation. This minus ax naught, this minus by naught, and this minus cz naught. These are constants because we're going to know our normal vector. Okay, we have to plug that in, and we have to also plug in our x naught, y naught, z naught. Okay, that's just a point that we're going to know that's on the plane. Okay, so these things are all going to be constants. They're not going to change. Okay, this isn't going to be anything that's going to be changed. It's going to be constant. Okay, now this ax, by, and cz, they are not constants. Okay, why? Because you have the x, the y, and the z. Okay, the x, the y, and the z, that's just going to be the whatever point else is on the plane. Okay, that's, you know, whatever point that you're trying to find. Okay, and, well, what you can do here is kind of group all these constants together. Okay, and you can just kind of say that that's equal to one variable. So watch this. We have an ax plus by plus cz plus d equal to 0. This right here is called the linear equation. And you may also see, okay, you may also see that this equation is written as ax plus by plus cz is equal to d. Okay, you might see that. You might see the d on the other side. It's really no difference, okay? In that case, that d that you'd be talking about would be the negative version of this d. So, you know, really, however you want to put it is fine. Now, I'm assuming you're confused as why did I group all these constants into one constant down here. That's literally just for the purpose of kind of cleaning it up, okay? Putting it down into this linear equation, literally just, I mean, it just cleans up all these constants, okay? This just becomes all one thing, which is that d. All right, so that's kind of the idea. Okay, we're just cleaning up, and that's how we get the linear equation. So kind of just a summary of what we did here. We know that we can't describe a plane with a point and a direction because then we just end up creating an axis for ourselves that we can rotate, you know, an infinite number of possibilities of planes around. Okay, so we need to describe it with a point and a normal vector. Okay, and if, you know, we see that from this whole picture right here, that if we dot our normal vector and the vector r minus r naught, we get 0 because these two things are orthogonal. This vector r minus r naught is on the plane, and, well, the normal vector is normal to the plane, or it's orthogonal to the plane, okay? And so you dot these, it equals 0. That's our vector equation, okay? You compute the dot product. That gives you the scalar equation, okay? Because when you compute a dot product, the dot product is a scalar. Okay, so this is why that's your scalar equation. It also, you can say, it does not contain any vectors. Okay, for, you know, further showing that it's a scalar. Now, all we did was we distributed the a, the b, and the c. We found which terms are constants. Okay, and we just kind of put that all into this plus d. Okay, just to clean it up a little bit, just to make it look a little nicer, and that gave us our linear equation. Okay, so, you know, that's the 3 equations for plane, and that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for vectors and the geometry of space in the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.